When I first saw this question, I didn't know it was honestly able to be solved, but it is. So let's try to solve this. We have 10 to the fourth plus 324 times 22 to the fourth plus 324 times 34 to the fourth plus 324 times 46 to the fourth plus 324 times 58 to the fourth plus 324 over 4 to the fourth plus 324 times 16 to the fourth plus 324 times 28 to the fourth plus 324 times 40 to the fourth plus 324 times 52 to the fourth plus 324. Wow. So yeah, when I first saw this, it was quite daunting, but there's actually this cool identity, and it's referred to and known as Sophie Germain's identity. And this is a very unwell known, identity. Not a lot of people study this. And it's just a very cool factoring trick. So basically what it is x to the fourth plus 4y to the fourth is equal to x squared minus 2xy plus 2y squared times x squared plus 2xy plus y squared, 2y squared. And this is Sophie Germain's identity. It's really pronounced Germain. Her name is French, so. All right, now let's see how we can, work with this. Well, notice in every single product, I have something raised to the fourth, right? So the base number is different in all of them. Like here it's 10, then 22, then 34, 46, 58. So all of those are different. But notice every single one has 324. Well, what's special about 324? Well, one thing is that I can rewrite 324 as being equal to 4 times 81. But if you know your powers well, 81 is equal to 3 to the fourth power. So I can say that 324 equals 4 times 3 to the fourth power. This looks very similar to what I have here, where my y is equal to 3. So what if I just generalize, right, and say x to the fourth plus 4 times 3 to the fourth. That's going to be equal to x squared minus 2xy. Now my y is 3, so that's going to be minus 6x. My y, once again, is going to be 18, so this is plus 18. And then times x squared plus 6x plus 18. Okay. Well, let's think about this really quickly, right? I have minus 6x and plus 6x. How can I get these to look more alike? Well, what if I complete the square within each factor? When I do that, this is going to become x minus 3 squared plus 9 times x plus 3 squared plus 9. Notice the symmetry that's going on here. And here's that 324, right? So now I can just take all my x values that I have. So for instance, I have 10 to the 24th is my first thing. So I can say 10 to the 4th plus 324 is equal to, all right, so that's going to be 7 squared plus 9, right? 7 squared plus 9 times 13 squared plus 9. 22 to the 4th plus 324 is equal to 19 squared plus 9 times 25 squared plus 9. And you can see this sort of forming together, right? So now if I do 34 to the 4th plus 324, it's going to be equal to 31 squared plus 9 times 37 squared plus 9. And I think it's important that I write all of these out. So now we have 46 to the 4th plus 324. It's going to be equal to 43 squared plus 9 times 49 squared plus 9. And then we have 58 to the 4th plus 324, which equals 55 squared plus 9 times 61 squared plus 9. All right, so that's our numerator, right? Now let's think about what our denominator would be. So I'm going to just label this here as that all of these factors are my numerator. Now let's go to think about the denominator. So notice my denominator factors. 4 to the 4th plus 324 is going to be equal to 1 squared plus 9 times 7 squared plus 9. 16 to the 4th plus 324 is going to be equal to 13 squared plus 9 times 19 squared plus 9. 28 to the 4th plus 324 is going to be equal to 25 squared plus 9 times 31 squared plus 9. Then we have 40 to the 4th plus 324 is going to be equal to 37 squared plus 9 times 43 squared plus 9. And lastly, we have 52 to the 4th plus 324, which is equal to 49 squared plus 9 times 55 squared plus 9. Now, look at this really carefully, right? I'm not going to rewrite out my whole numerator because it's going to take a while to plug everything back in. But just think about this logically, right? These are all factors being multiplied together. Here I have my numerator and denominator. Look at the pattern here, though. I have a 7 squared plus 9 in my denominator and the numerator. I can say that those cancel out. I have a 13 squared plus 9. I have a 19 squared plus 9. 25 squared plus 9. 31 squared plus 9. And what this problem did is the people who invented it, they specifically chose these factors and numbers. So the problem would be neat like this. And now you can notice that all of these factors cancel out. But not all of them. Notice what I'm left with. In the numerator, I'm left with 61 squared plus 9. And then my denominator is 1 squared plus 9. Now all we have to do is evaluate this. So we need to get this into, you're going to see there's a very nice result here because this is going to be 10, right? So here I have 10. Now my numerator, okay, I have to figure out what 61 squared is. Now, an easy way to do 61 squared quickly in your head is you go down to the nearest nice number, I like to call it, and then up however much you want down. So for 61, what I'm going to do is I go down to 60 and up to 62. You multiply those, and then however you went up or down by, you square that. So plus 1 squared. And this is a trick from Arthur Benjamin. You should go check him out. And now I can do this in my head. 60 times 60, 3,600. Plus 120 is going to be 3,720. Plus 1 is going to be 3,721. And then don't forget I still have a 9 here. So that's going to be 3,730. So now look at how nice this is. I have 3,730 over 10, which equals 373. Wow, what a problem. And this is why, Sophie Germain's identity is so powerful for problems like these, because you're not going to, be able to, evaluate all of this. It's just way too much. So this is where, very advanced factorization techniques come in, and if you can recognize these patterns, you'll be better off.